Hello, everyone. This is the lecture for section 3.2 to 3.6 for our Math 210S portion, quadratic functions, polynomials, their zeros, and their graphs. So this is collapsing a fair amount of chapters from our pre-calc material all into one section, okay? This one's going to be very heavily Desmos-based. There's a lot of sort of underlying concepts or underlying sort of computation that I'm going to sort of excuse away, not exactly excuse away, but I'm going to overlook in favor of having you all use Desmos instead, okay? For this section in particular, what we're going to be doing is quadratic functions, the polynomials, right? See the different ways that we can present quadratic functions and polynomials, right? And then see how they relate to their graphs. Okay. All right. So the first thing that I want to move on to, so the very first set of functions that you are all familiar with, right, in terms of how to demonstrate any sort of information, right, is lines. The next more complicated one are quadratic functions. And those, I'll get to them in a second, are functions of the second power. So something in there, the variable in particular, the variable x is going to be a second power, okay? For quadratic functions, there are two general forms that you'll be able to see. The first one is this one, the ax squared plus bx plus c, okay? And the standard form, okay, is usually an x minus h squared plus some k value, okay? And all of those values, the a, b, c, and the a, h, k for the standard form, right, they are real numbers, okay? They can be any numbers you could possibly wish, okay? There's a couple things that I do want to point out for all of these, right? So the first one, if a is bigger than 0, okay, the shape of these graphs, I'll get to the shape in a second when we do our example. The shape is called a parabola. It's a U shape, okay? If a is bigger than 0, then it opens upward, right? And there's this thing called the vertex, okay? And the vertex becomes a minimum for the graph, okay? Everything's in reverse if the a is less than 0. So if your a is negative, right, then it opens downward, okay? And the vertex becomes a maximum, okay? X-intercepts, just like I covered when we did lines, right? The x-intercepts happen when your y, right, is equal to 0, right? Uh-oh, got it. When the y is equal to 0, I'm going to do this. Y, we know that this is equal to an f of x, right? And that's equal to 0. In order to solve this kind of thing, for lines, solving this is easy enough, right? But for quadratic functions, we have this thing called the quadratic formula. Hopefully you guys remember. There was a song with it, set to Ring Around the Rosie, I believe it is. This is it in general, okay? The B's, the A's, and the C's match up to this A, this B, this C, okay? Okay. And the last thing, the equation for the vertex. So there's this thing called a vertex for these functions, okay? It's usually given by h and k. It is this h and this k, okay? That h and that k, okay? And they can be rewritten as this, right? The h can be minus b over 2a, and the k can be the f of h, right? Once you solve out the h from the previous portion, right? Which is also equal to the f of minus b over 2a, because that's what h was equal to. Okay, what I want to sort of impose on everybody, right, is that both of these forms, the standard form and the general form, right, they are interchangeable. They are interchangeable things. So I can grab the general form and turn it into the standard form, right, and then I can grab the standard form and turn it into the general form, okay? In many cases, one is harder to do than the other, as in turning into standard to general and general to standard, right? Uh, Changing it from one form to the other tends to be difficult in one direction, right, and easier in the other, right? But more importantly, right, uh, both forms give you the same exact information, just in different methods or in different ways. Okay. Okay. So now let's go on to the example. So let's take our Steph Curry example here. Okay. Uh, Steph Curry shoots and makes a three-pointer, and the horizontal velocity is given by this. Okay. The height of the ball is given by that function right there. Okay. So first of all, what we're going to do is find and interpret in words the vertex of h of t in the context of the problem. Okay. So first of all, what I'm going to do is I'm going to bring in Desmos really quick. Okay. And we're going to graph it. Okay. Negative 16, and let me actually do h of t. So we know what we're doing here, right? H of t is equal to negative 16t squared plus 21.5t plus 9. And there we go. We have our function, right? Okay, I'm going to get rid of this really quick. And I'm going to sort of, I'm going to be pressing shift so I can do the special zooming. There we go. So this is the trajectory of the ball. This is the trajectory of the basketball. Okay. So two things I want to share with you guys, right? This is the parabola. This is the shape of a parabola. If you take a look, right, the function from the very beginning had a negative, so the U shape, right, should be facing downward. And it is. Cool. Okay. More importantly, right, we have a vertex. The vertex is this tippy top right here. Okay. And if you click on it with Desmos, it'll give you the exact coordinate, right? But what we want to do, what I want to do, is at least try to solve these by hand and then use Desmos where we need to compute. Okay. All right. So that's what we're going to be concentrating on right now. So first of all, find and interpret in words the vertex of h of t in the context of the problem, right? So for h of t, right, the vertex, that is the h and the k. So the first thing, this is practically the steps right here, right? Step 1, find h. Step 2, find k. So I'm going to do, and actually I wrote that in sort of a bad spot. I'm going to pick it up, move it over here. There we go. Okay. No, not what I wanted. Come on. There we go. So first step, find h, right? We know that that is the minus b over 2a. Here's b, here's a. So we get to plug that in flat out, right? So equal to, and actually let me move this down here, is equal to minus 21.5 divided by 2 times my a, which is the negative 16. Make sure you carry along that negative that's up front. Okay? And I'm going to go ahead and use Desmos for the mathy parts here. Let me get Desmos back out. Negative 21.5 divided by 2 times negative 16. There we go. This gets us our 0.67. Let's bring that back. 0.671875. 0.671875. Okay. So that was H, right? For K, right, that is essentially F of H, right? So that means we get to plug in this thing. Okay, we get to plug that in to our function itself. Okay, so that's going to be negative 16.67. I'm going to say 0.672 to round it away. And this is fine. I think I've mentioned multiple times in the class, If you round 2 decimal points, 3 decimal points, I think that's healthy enough. This isn't a science class. I don't entirely care about sig figs, okay? So I'm going to go ahead and plug this in. Squared plus 21.5.672 plus 9, okay? And I'm going to go ahead and show you guys again, right? The reason why I like Desmos. We defined h of t already, right? You guys see that? I can go ahead and just do h of that exact point, right? 0.672. And it gives me the thing that I want, 0.6722222, right? 16 point, whoops, let me actually, because I'm going to need this space right now. 16.22, I believe in change, was it? 222. That's cool. Okay. All right. So numerically, we found our values. Okay. Numerically, we found our values. Okay. We know that the h and the k are going to be this, right? 0.672, comma, 16.22. This is our numerical answers, right? But the part that we're missing here is this bit right here. Solve in the context of the problem, right? Okay. So that comes, to do that, right? We have to interpret these. We have to say it in words what each one of these values are, right? So if you take a look, right? Let's go ahead, go back to the graph. The stuff down here, the stuff on the horizontal axis, right? That is our time, right? And the stuff on the vertical axis, the axis that goes up and down, that is our height, correct? That was the point behind the function, right? That I gave it a time, and it gave me a height. Okay, that's all we need. Okay, so what we get is this, right? At 0.672 seconds, right? Seconds. Ball, let me do this. Hits the max height of 16.22 feet. And we are done. Okay. And let me highlight this right here too. There we go. Okay. So that's exactly what this vertex is because of all the explanation that I gave above, right? This is a parabola. The negative up front makes it open downward, so it's a downward U shape, right? So that means my vertex should be a maximum of some sort. This is the maximum. Now, like I said, Desmos can double check all this stuff for you, at least computationally, right? So if we click up here, we should get, there we go, 0.67188, comma, 16.22266. Okay? So we got it right. We're good. We are awesome. Okay? Again, when you're doing this on your own, you're more than welcome to use Desmos however you need to. Okay? All right, next question. When does the ball go through the hoop, which is 10 feet tall? And when does the ball hit the ground? Okay? If he airballs, of course. If he airballs. Okay? Actually, you know what? Yeah, I'm going to go ahead and get rid of this one in the interest of time. Bam. I just want to do the 10 feet tall one. This is, I think, the more important bit. Okay? When does the ball go through the hoop, which is 10 feet tall? So we want to find out, right, when the height of the ball is 10 feet, right? When the height of the ball is 10 feet tall, right? So that means I want minus 16t squared plus 21.5t plus 9, we want that to be equal to 10 feet, right? Because this right here is the height of the ball. We want it equal to 10 feet, right? Okay. All right. So there's a little bit of math here, a little bit of arithmetic that we're going to need to do. And the thing that we're going to do is, I want this side, the side with the 10, I want it to be equal to 0. And there's a reason for it, okay? And I'll come back to it in a second, okay? But for now, right, I'm going to do minus 10, minus 10. Everything else is still the same, right? So I can do minus 16t squared plus 21.5 t. 9 minus 10, that should be minus 1, is equal to 0. So I'm going to concentrate on this now. Okay? You guys see this thing right here? The thing with the hot pink that I'm sort of highlighting or underlining there? Okay? It disappeared, this thing. Okay? This right here requires quadratic formula. I'm going to write it down here. Requires quadratic formula. Okay, and that is the thing that gave us the little song. Okay, the minus b plus or minus blah 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 blah. Right. Okay. So I'm gonna go ahead. I won't compute it. I'm gonna let Desmos compute it, but I'm gonna show you guys what I'm gonna be plugging into Desmos. Okay. So I'm gonna write it way over here. So x is equal to. I'm gonna just write the equation first of all. Minus b plus or minus, right? The square root b squared minus 4ac all over 2a. And I'm going to use the a, the b, and the c that are present right here. Okay? So minus 21.5 plus or minus the square root 21.5 squared minus 4. Let me get rid of the, come on, there we go. Minus 4a minus 16. C minus 1. I'm going to extend the square root, and this is just my thing, and hopefully you guys use it too. Whenever I have a square root, I like to leave a little tail. Let me put the tail back in there. There we go. I like to leave a little tail to say that that is the end of my square root, okay? It's super easy to let the square root overextend to something you don't want, so I usually say this is where it stops, okay? All over 2 times a, which is in this case minus 16, okay? This will get you 2 answers, okay? So what I want to do now is I want to throw this all into Desmos so you guys can see what I'm actually doing, the results I get, okay? So I'm going to leave it there, right? Minus 21.5 plus the square root, and use parentheses sparingly, right? 21.5 outside squared. Actually, I'm going to open this up a little bit so you guys can see the rest of it, okay? Minus 4 minus 16 minus 1, and I'm going to put all of this in parentheses, all divided by 2 times negative 16. Okay, so notice what I have here. I have 2 answers. I'm going to have 2 answers, right? I'm going to move this over just a smidge. There we go. Okay, this positive answer is the one that's currently on the screen, right? The positive answer, and I'm going to go ahead and let me do this. I'm going to have to, there we go. The positive answer, right, that is 0.0482, okay? And I'm going to get a negative answer as well, so I'm going to go ahead and go into my math here in Desmos and just hit negative there. And I got 1.2955, 1.295. Okay, and these are seconds. So let's go back to the question at hand, right? So the question originally was, when will the ball go through the hoop, which is 10 feet tall? Okay, now let's go to Desmos now. Whoa, bam. Okay, I'm gonna squish this a little bit. So you guys see here is 10 feet. Let me do y equal 10. There's the line at 10 feet, right? Now, if you guys have ever watched the basketball game, right, this point right here is not where the hoop is, right? This is where the hoop is, way over here, okay? And there you go. We double checked our work using Desmos, right? Like I said, I want you all to, whenever possible, right, compute the answer out. Always, always, always double check using Desmos. Okay, and this is excellent because look at the x values, right? We got our 0.048244, and then we got our 1.2955, right? Which was the two answers we were supposed to get. Yay! Okay, all right, moving right along now. Okay, I've got some quick checks for you guys to try out. Okay, this one deals with cannonballs fired off of a cliff on different planets, right? Half of you are going to do planet X, half of you are going to do planet Y. Okay, and you guys are going to see what I mean by mapping this out. A lot of the stuff in physics, actually, at least the first semester physics, can be mapped out using quadratic equations. Okay, so we'll take some time with this one. Okay, moving on. Now I want to cover polynomial functions as a whole. Polynomial functions as a whole. Okay. So quadratic functions, right? The original one, I'm going to put down the one that we know for now, okay? Ax squared plus bx squared, that's supposed to be a square, my bad, squared plus bx plus c, right? This is a polynomial function of second degree, okay? The more general polynomial function, okay, they look like this. It's this long thing right here. So this is basically saying, right, a polynomial function is where that power, this power in particular, this one right here, the n, right, can be as high as you want. Okay? And a polynomial function tends to have exactly how the quadratic, but it's just way more of them. So there's going to be an x to some power times some number, right? And it's just going to be listed pluses or minuses all the way down. Okay. Each one of these little pieces, right? So this piece, this piece, this piece, this piece, so on and so forth. Each one of those is considered, or it's called, the term of a polynomial function, right? So when we say the squared term, it's that one. When we say the eighth power term, right, we're looking for the one that's a 8x to the eighth. We're looking for whichever thing that thing is, right? All right. Now let's get into some key terminology and key sort of info for a polynomial function, okay? I'm going to try to keep that on the screen, okay? The an is what we call the leading coefficient. ENT. The highest power, the n, is called the degree. Okay? The degree tells us the number of x-intercepts that our polynomial is going to have. Okay? Okay. And then altogether, that an xn, the highest, the absolute highest power term, right? All of that is called the leading term. Okay. There's a lot of stuff built into just that leading term, okay? And this is what is built into it, okay? Even powered leading terms have this kind of shape. They have a U shape of some sort. Okay, and these are a little, how could I say this? These are a little misleading, okay? In actuality, what I want to say is this, right? That if your leading term is even, it's going to do something like this. It's going to come from, whoa, let me actually do it with the blue pen, and I'll do it nice and thick. There we go, and not leave a dot. There we go. It's going to do something like this. It's going to come from way up here, and then it's going to do a couple bounces. I don't know what it's going to do in the middle, but then at the end, it's eventually going to just start shooting upward. These are even powered functions. These are where the leading term is an even power, right? So something that has as the biggest power x to the 100th power, right, will have this kind of behavior. All right? Okay. Opposite, odd powered function. So if you have an x to the 57th, an x to the 13th, right, they will have this kind of behavior on the right-hand side. Okay? And again, this is sort of a misnomer, or this is sort of, the picture at least is a little misleading. What tends to happen is this. They're going to come down from down here, right? And then do a little bit of bouncing in between, and then eventually just start heading upward, shooting upward after a certain extent. Okay? This is the behavior for odd-powered leading terms. Okay? All right. We are getting there. We're getting there. Okay? Okay, so just keep this in mind because this is going to become very helpful once we get down to graphing at least a little bit. Okay? Okay. Definition. We know that this is a polynomial function, right? Any polynomial function can be rewritten as this, at least for this class. It can be rewritten as this. So basically saying that I can grab my, my polynomial function, right? And I can split it up into what's called monomial terms, okay, to a specific power. Notice how each one of these is, so B1, H1 to the P1. All three of those things are sort of together, clumped up, right? B2, H2, P2. So B2, H2, they're the things that are inside, right? And then to the power P sub n, whatever that thing is, right? All the way over, right, to Bm, Hn, M to Pm, right? Okay. This one down below, that is what's called the factored form. And that contains a lot of information, okay? First of all, the first bit of information is this, that if you know the degree of the polynomial, if you know the highest term that is in your polynomial, right, then all those powers that came within the factored form, they have to add up to it. Okay? They have to add up to it. Okay? Okay, so one more definition. Suppose we take a given factor. So suppose we take one of these. Suppose we take either, like, wrong, too big. Suppose we take one of these, this one, or this one, or this one, right? Suppose we take any one of those, okay? And we look at the power, okay? Suppose we look at the p-value, right? The number of times k that a given factor appears in the factored form of a polynomial is called its multiplicity, okay? And what we're looking at here is the pi, right? Let me actually write it down, looking at in the factored form, okay? This is what we're looking at, those powers in this form in particular, this one. Okay. All right, so there's a fair amount of nice stuff that we can pick out from the factored form from each multiplicity. Okay. And this is it. Whoa, there we go. Okay. Uh, Single zeros, right? Or when the multiplicity is 1, right? P1, this is what it's going to look like. It's going to cross. Okay. Multiplicity 2, so if P is equal to 2, this is what it does. It sort of touches it and bounces directly off. Okay. Multiplicity 3 does this little curve thing. Okay. But it crosses. It outright crosses, right? Okay. And this is the general idea. So even multiplicities. Whoa. Even multiplicities just sort of touch or bounce, right? Odd multiplicities outright cross. Whoa. Okay. And that's what we're going to be using right now. Okay. So what does this all mean, right? How does this all work? That's the example that I want to cover right now. So I've got a function here. I've got an f of x. Okay. I'm going to attempt to graph it. Okay. And what I'm going to do, I'm going to get rid of these in particular. So I'm going to get rid of the 5, the 10. Turns out, since this is a rough sketch that I'm going to be providing, I don't need those. Okay. All right. So the first thing I'm going to do is I'm going to list the factors. Okay. List the multiplicities of each 0. Okay. The behavior of the graph at each 0. And then I'm going to provide a rough sketch. And I'm going to use my graphing utility. I'm going to use Desmos to verify my results. Okay. Okay. To do this, right, I'm going to do this. I'm going to create a table here. Okay. It's going to be like this. Factor 0, multiplicity, and then touch cross. Okay, just so that we can get our thoughts organized. We don't lose ourselves, right? Okay. So the first thing I'm going to do is I'm going to grab the factors. In this case, there are 3 of them. 1, 2, 3. So 2x plus 3. The next one down is x minus 5, and then the next one down is x minus 1. Okay, so now the zeros. This is the zero or the x-intercepts, right? You guys remember that? Okay. To find the x-intercepts, we make each one of these equal to 0, solve it out. So if we do 2x plus 3 equals 0, right? We get x is equal to, so move this over, divide by 2, minus 3 halves. Okay? Next one. X is equal to 5, and the next one after that, let me put it right directly closer to this, right? The next one is x equal 1. Got it? So those are our zeros. One of them, x is equal to the very first one, negative 3 over 2. The next one is x equal 5, and the next one after that is x equal 1. Okay, we're getting somewhere. Multiplicities. Okay, now we're looking at these powers. Now we're looking at the powers. So this one's got a 2. It's not written here, but this one has a 1. So I'm going to stick in a 1. I'm going to highlight it, and this one has a 3. So the multiplicity is 2, 1, 3. Okay, and now I get to decide the behavior. As you saw from before, right? If the multiplicity is even, it bounces off, and if the multiplicity is odd, it'll outright cross. So since this one is even, this is just a touch, right, or a bounce, right? And then the other two are cross and cross. All right. There's one more thing that we need in terms of information so that we can outright graph this thing, okay, at least provide a sketch, and that is the power of the polynomial, okay? And we know this. We know what the power of the polynomial is, right, or the degree of the polynomial. We add up the powers. We add the 2, the 1, and the 3, right? So my n is going to be 2 plus 1 plus 3, and that is 3 plus 3, 6. So we know that this function right here is a 6th degree polynomial. One more thing of information. Okay, I know I keep saying there's one more thing, one more thing, one more thing. You see there's this negative up front. I highlighted it in pink, right? That negative tells me it's going to be flipped. Okay, so we know that the general shape of a 6th degree polynomial starts off up here, right? Comes down, does some business, and then whoosh, right? Let me put the business back in. There we go. Make sense? This is the overall shape of a 6th degree polynomial if it was positive. If it's negative, it does the opposite. So there's still going to be the business in between, right? But instead of starting up and heading back up, right, it's going to start from down below and come downward. There we go. All right. So here we go. I need to graph all of this information, all of this, right? So let me recap real quick. We need a 6th degree polynomial, right? That's faced downward, that touch and cross, right? At these specific x-intercepts. This is a little bit more advanced and connect the dots, but I think we can all handle it, right? So let's try it out. So I'm going to put down my points. I'm going to put them down in the hot pink. There we go. Okay. One x-intercept is going to be negative 3 over 2. So 1, negative 3 over 2, that's about a half right there. Okay. The next one is at positive 1 right there. And the next one after that is at 5. Okay, so we at least have the x-intercepts down, right? Next up, behavior. Touch and cross, right? For this one, it should touch. For this one, it should cross. And for this one, it should cross. Right? But because of this information, that it's a 6th degree polynomial, right? It's got to end up going down this way, and it's got to end up going down this way. Right? Now you get to play connect the dots a little bit. Okay? So I'm going to keep it blue. I'm going to make it actually a little thinner. There we go. So my guess is the function is going to do this. It's going to touch this one. Whoa. Out of all days, right? Okay. Touch this one. Come back down. Cross this one. So notice how I'm crossing it, right? And then it's going to cross this one. There we go. Notice that our function, the function that I drew, right, has everything we want. It is a 6th degree polynomial, right? It's faced downward because it's a negative, right? It's crossing the x-intercepts where it's supposed to, and it has the appropriate behavior from the touch cross column. Got it? Okay. When you do this on your own, I am not expecting exactness. I do, though, expect that you can pick out the behavior from each one of the bits of information from the function itself. Okay, and no matter what, you can double check all of this through Desmos. So I'm going to grab this. I'm going to move this over. I'm going to open up Desmos real quick. I'm going to get rid of the stuff from our previous example. Okay, and I'm going to go ahead and type that function in. So f of x equal negative 2x plus 3 and square it, x minus 5, x minus 1. Now, I'm going to make this big now. Okay, you guys can see how it's not, there we go. We're missing one, there we go. I'm going to grab this, squish this down a little bit. Look at that. There we go. Okay, so let's take a look at my guess and the actual graph. Not bad, right? Not bad at all. So look at so this is something that I do want to point out. I'm not expecting exactness, right? So you guys see how high I made it, right? I don't expect it to be exact, right? But I do want you to be able to confidently and accurately discern the shapes of these functions just from the factored form. Okay? Whew, that was a lot of information. That was a lot of information. Okay, I believe after this is some quick checks. I do want you guys to practice it. Okay, try these out at home if you want, but I'm going to concentrate more of our time in class to solving them out. After that, it's lecture questions. Okay, if you have any other questions on the stuff that I just covered, come see me during my office hours. Ask me during our quick check time, or find me in the math lab. Okay. Besides that, happy studying.